everybody. In this week, you're going to see what is sampling distribution and how to estimate confidence interval using normal distribution. So in part one, you will see how to recognize the concept of sampling distribution, how to distinguish between different sampling methods, how to explain central limit theorem, how to state a sampling distribution and its standard error, and how to transform a sampling distribution to a standard normal distribution and use it to solve problems on sampling distribution. Okay, so let's start from population. When a population is to be investigated, a part of the population is chosen and it is known as sample. And the process by which you choose a sample from the population is known as sampling. For a sample will most likely have a similar characteristics of a population. For example, mean of a sample X bar can give us an approximation of the mean of its population. Yeah. So sampling is used to estimate the characteristics of the population. A sample is usually smaller than its population. Now, can you think of some advantages why we study on a sample rather than a population? Good. Yes, it saves our time. It's quicker to investigate. It is cheaper to investigate a sample, more convenient and accessible, and it can be more appropriate. That is, data from the sample can be used to make a statistical inferences about the population as a whole. So you can use the sample mean to estimate the population mean. The process of taking a sample needs to ensure that the sample is unbiased, just to avoid any bias, is a representative of this population, and is precise. That is, it accurately represents a population so that repeat samples are consistent with each other. These depend on two factors. One, how you choose the sample, that is the sampling method, and the size of the sample itself. Okay, so let's first see the sampling methods. Yeah, how you choose a sample. So we're going to concentrate only on two of the sampling methods. That is systematic. We'll start with systematic sampling. Systematic sampling, as the name says, you choose the member of each member of the sample systematically. For example, I have here some colored candidates who are standing in a row, and I'm going to number them. And I decide to choose every third member in the row. Okay. So what I'm doing here is I'm systematically choosing the member for my sample. So if I choose every third member, that means I am going to end up choosing only the purple candidate. So each member of a sample is selected at regular intervals of the population. So what I'm doing here is I'm being biased, yeah, because only purple candidate is chosen, yes. But since it has a predefined interval and hence it saves our time. So I save my time by choosing the purple candidate, that is every third member, because I am choosing based on a predefined interval, that is the third member. So this systematically choosing a member for the sample is called systematic sampling. So to avoid a bias, one good method is simple random sampling. Yeah. So here, each member of the population has an equal chance of being selected. For example, if I write down your names in a piece of paper and drop it into the hat, and I pick one of your name randomly, then each one of you has an equal chance of being picked. So what I'm doing is I'm avoiding bias, any type of bias. So systematic and subjective selection are avoided. This approach helps the sample to be representative of the population. However, if the sample is too small, it is likely that it won't be a representative of the population and will not give us a precise statistical inference for the population. Yeah. So it is very important that this method you choose for sampling is representative of the population and the characteristic of the sample precisely estimates the characteristics of the population. Okay, let me take an example to understand this sampling distribution. Okay, so let's say our task is to survey the weight of adults in a population. So given that we do not know the population mean. So let's say that we don't know the average weight of the whole population. Okay, we don't know mu. That is, mu is unknown. Mu is unknown. We don't know. Okay, how will you determine the population mean then, or how will you estimate the population mean? What you can do is you can take the sample mean, and from the sample mean you can estimate the population mean. Let's say that's your sample 1, and for a sample size of 9, you can estimate the sample mean to be x bar 1 for the sample 1. Okay, you know how to find the sample mean. We have done that in week 1. You take the weight of each adult, add them, and divide by the sample size. Divide by the sample size, which is 9 here, and you get the sample mean. Okay, so similarly, you take another sample, take the weight, sum it up, sigma x1, x2, so sigma x1 plus x2 plus x3, so sigma x divided by 9 will give you the sample mean for the sample 2. Similarly, for the sample 3, you'll get the sample mean x3. Similarly, for sample 4, you get a sample mean x4. So now you have a series of sample mean here. A distribution of this sample mean is called sampling distribution. So what is a sampling distribution? It is the probability distribution of a statistics. Here it's a sample mean calculated for random samples of a given population to estimate the unknown population mean. Or sometimes the population mean is varying with time. Again, you can use the same technique. So you take the sample mean of different samples for the same sample size and then use it to estimate the population mean. And this distribution is known as sampling distribution. Okay, now what if we increase the sample size? Okay, so as you increase the sample size, you know that the sample is more likely to represent the population because the sample mean will get closer and closer to the population mean. So let's take an example to understand that, okay? So let me say these are the heights of some adults, okay? And we know the population mean now, which is around 168. So now if you take a sample size of 2, so say 169 and 171, yeah? And what will be the mean of this 170? So your mean will lie somewhere here, yeah? Similarly, I'll take another sample or a size of 2 again. So 176 and 180, so sample mean will lie somewhere here. Similarly, I'll take few more sample of size 2, just 2 data values in the sample. I will get a range of sample mean around this. So it could be anywhere from 154 to 182, yeah. Because I have value till the largest value is around 187, yeah, 188. So it can go anywhere from this to this because the sample size is small. Sample size is 2. And the mean of this will be somewhere in between here. Yeah. Now, if I increase the sample size to 8, let me take all these bold numbers. I may get a sample mean of around 171 point something, yeah. And what will you see? When the sample size increases, the sample mean, for example, here, the sample mean is somewhere here. Now, I'm going to increase the sample. So if you determine the sample mean, it gets closer and closer to the population mean. So if I increase the sample size, you should try that. What I want you to do is, for a sample size of 20, just take randomly 20 data values, add them all and divide it by 20 to find the sample mean. And check, add any data values, 20 data values, yeah, and find the population mean and check whether it's almost close to the population mean. You will see that as you increase the sample size from 2 to 8 to 20, the sample mean gets closer and closer to the population mean. Okay. Now, when we take repeated random samples from a normal distribution, where each sample has n data values, and if X bar is the mean sample of each sample, mean of each sample, that is, as you increase the sample size, you can see that from sample size n is equal to 2 to 9 and 9 to 25, you can see that the spread of the values for the mean of the sample tightens. That is, the sample mean is getting closer and closer to the population mean. And this is called central limit theorem. That is, what is distribution as the sample size gets larger? Yeah. Okay. So what I'm trying to tell you is, if you take repeated sample, each of size n, you get different sample means, as we saw in the previous example, x1, x bar 1, x bar 2, x bar 3. And the distribution of this probability with sample means on either side of the population mean is called sampling distribution. And the sampling distribution is stated as follows. That is, X bar is a random sample that follows a normal distribution with the population mean mu and a standard deviation of sigma square n. So that is what you should see the difference here, okay? So this was the normal distribution of a random variable. This is the normal distribution of sample means. Okay, so a sampling distribution has a standard deviation of sigma square by n, where n is the sample size. Okay, let me write it neatly here. So this is known as sampling distribution. This is how a sampling distribution is stated. And the standard deviation for sampling distribution is the square root of the variance. here the sampling distribution, the variance is sigma square by n. So standard deviation is square root of that, that is sigma by root n. And this is also called standard error. Okay, it's very important you know that. So as you increase the value of n, standard error decreases. Yes, because n is in the denominator. Okay. Therefore, if a population has individual values distributed in such a way, for example, if I say that you have a random variable x that follows a normal distribution 14 and has a variance phi square, the sampling distribution is stated using this, and the standard error will be stated as sigma by root n for a sample. So let's say the random sample size is 10. Okay, let's say the sample size is 10, and then the sampling distribution will be x bar is a random variable that follows a normal distribution, random sample mean, sorry, not variable, random sample mean that follows a normal distribution with a mean 14 and a variance phi square by 10. And what is the standard error here? Standard error is phi by root 10. Okay, so you can, this is the standard error or the standard deviation of the sampling distribution. Okay. Okay. So what would be the sampling distribution and standard error for the sample size 30 for the same distribution? Good. It's going to be 14 comma phi square by 30, and the standard error is going to be phi by root of 30. Okay. Now, for a sample size of n from a population, the sampling distribution is given by, choose the right answer. Good. The quantity sigma by root n is known as, good, both A and B. It's known as standard error and standard deviation of the sampling distribution. Okay, now let's see how to transform. Yeah. Okay, for sample size n of the sampling distribution, we know how to state a sampling distribution. Now, this is a normal distribution. Therefore, it can be transformed to standard normal distribution in the same way we have done before. It's not new to you. We can do it in the same way, except that the standard deviation was for the random variable there. Sigma was the standard deviation for the random variable. Now you have to take the standard deviation of the sample mean. So which was from here. Yeah, it is sigma by root n. So that's going to be your standard deviation. Look at that. So this is your random variable, and this is your random sample mean. It's a sample mean, yeah. And this is your standard deviation for the sampling distribution. Okay. Similarly, note that the standard deviation of the sampling distribution is different, yeah. Okay. Now, since I have said that, now I have to. So consequently, we can determine the probabilities associated with sampling distribution, just like how you did before. Yes? Okay. So we can transform the distribution. Now try this, guys, for x bar to a standard form using which of these relation? Choose the right answer. Good. That's true. The standard deviation for a sampling distribution is sigma by root n. Be careful there, yeah? That's for the sample mean, x bar, yeah? Okay. Now, I want you to fill this table. I'll do one for you. Find the sampling distribution and transformed Z for each of the following. So let's do one together. So let's do A. Okay. So here you can see a normal distribution. So the population mean is 27 and sigma is equal to 3. And the sample size n is equal to 9. Now, what is the sampling distribution? Sampling distribution is going to be 27, yes. Sigma is 3 square, yeah. So you have to find sigma by root. Sigma by root n is a standard error, so be careful there, yeah. So it's going to be, I should have copied and pasted here, okay. Okay, so this is what you're going to do, okay. So sigma square by n. So what you do is, you can write 3 square or you can write 9, it's up to you. By root 9, so it's root 3, isn't it? Let me show you what it is. So, yeah. Okay. So x power minus 27 by 3 root 9. So you're just going to, yeah, there I have given it. So you have to use that formula, and z is nothing but x bar minus mu by sigma by root n, because it's the square root of this quantity, yeah. So square root of sigma square by n. Yeah. Okay. So now I want you to fill these unknown values, yeah. Okay. Good. So, okay. Good. Yeah. Okay, now one more question. A manufacturing process produces components whose length L millimeter is believed to be distributed as this. That is, L follows a normal distribution with a mean 160 and sigma is equal to 4 from this. Yeah. What is the probability that the sample of 17 components will have a mean greater than 160 millimeter? So you have to just use the transformation formula and find the value. Good, it is 0.5 because look at that. You substitute the value, which is 160 minus 160, because population mean is also 160, divided by 4 by root of 17. So that's equal to 0. And the probability for less than 0 is 50%. Okay. Okay, that's it. So that's all for now. See you in part 2.